Hello, everyone. Good morning.
Hello, good morning.
Hello.
Oh, good morning.
Alec? Good. Just 1 minute, I'm going to get some coffee. So.
Hello, hello. Nice to introduce Professor Bonacci, also from University of Split. Hello, Professor.
Dobar dan.
Oleg,
Yep.
what do you think? Maybe you can be moderator and we can start the conference. And I expect that other people will join to us and participate.
Okay, sure. So first of all, thank you to all participants to join our seminar, one-day workshop. It's a pleasure to be a host of this event. And at the beginning, let's start with the welcome speech devoted to the Professor Blaž Gotovac. So since we have an agenda, maybe Professor Hrvoje or Vedrana will say a few words. Oh, even Professor Blaž is here. So welcome, Professor Blaž.
They lost, but I expect them very quickly. Da, čujemo se.
Hoćemo onda početi.
Može, počnite vi.
Dobar dan. Dragi Oleg, zahvaljujem za ovu organizaciju. Evo, ja ću ukratko samo dati jedan pregled od, ne znam, prije 45 godina kada smo počeli se zanimati za metodu R funkcija. Došli smo do atomskih funkcija na kojima smo se zadržali do danas. Počet ću sa atomskim funkcijama algebarskog tipa, koje uglavnom svi dobro znamo, koje su i najbolje izučene i najviše se i primjenjuju sada. Znamo njihova osnovna svojstva, beskonačne derivabilnosti, finitnost, što je jako važno za numeričku primjenu. Nadalje imamo klasu funkcija trigonometrijskog tipa koje su najslabije izučene iz ovog područja. Znači njihovo vrijeme tek dolazi za detaljnije upoznavanje. Ovdje vidimo jednu funkciju također finitna sa nosačem -1 do +1, frekvencije pi, i vidimo kako su razigrane te derivacije koje moraju u svakom sljedećem koraku deriviraju sinus, dobivamo kosinus, dakle linearna kombinacija ove finitne funkcije daje trigonometrijske funkcije različitih frekvencija. Vidimo ovdje za frekvenciju 0, zapravo radi se o algebarskoj funkciji koja razvija jedinicu. Ovdje ona razvija polinom do 1. stupnja. Ako se frekvencija poveća na 2, dolazi do značajnih promjena u samoj funkciji i u njezinim derivacijama. Također, kod frekvencije 3 bitna je razlika, samo za jedan je povećana frekvencija, oblik derivacija se značajno promijenio. Treća klasa funkcija eksponencijalnog tipa na kojima smo dosta radili i koje su izučene negdje na pola između algebarskih i trigonometrijskih, to su funkcije eksponencijalnog tipa. U tom vektorskom prostoru funkcija eksponencijalnog tipa sadržane su algebarske atomske funkcije iz vektorskog prostora UP. Dakle, to je podskup ovih eksponencijalnih funkcija. Koja je njihova karakteristika? One imaju sličnost sa algebarskim funkcijama, računaju se u binarno racionalnim točkama s jedne strane, s druge strane imaju tenžni parametar ili frekvenciju kao trigonometrijske funkcije koje omogućavaju njihovo naginjanje u desnu ili lijevu stranu, što im daje dosta bolja aproksimacijska svojstva od algebarskih atomskih funkcija. Izračunavanje ovih funkcija je analogno o izračunavanju algebarskih i mi smo preferirali računanje funkcija pomoću linearne kombinacije njihove materinske funkcije up. Funkcije ovdje je e-up kod eksponencijalne. Kod algebarskih koeficijenti linearne kombinacije u ovom izrazu su brojevi, a kod eksponencijalnih su to izrazi koji su utoliko složeniji, utoliko više ima posla. I vidimo, rećemo, za frekvenciju 2 ili ovaj tenžni parametar, da je funkcija nagnuta u desnu. Ovo su funkcija i njezina prva i druga derivacija. Vidimo razliku od algebarskog FAPA 2. I sad nešto samo o R funkcijama. Boolova algebra koja se primjenjuje tu i polualgebra koju je konstruirao Vladimir Logvinovich Rvachev su izvanredna podloga za pretraživanje područja i za definiranje područja. Tako da možemo područje praktički proizvodnog oblika analitički odrediti. Također, pretraživanje područja uz granicu i u cijelom području je vrlo brzo i jednostavno. Evo u prostoru. Međutim, daljna primjena metode R funkcija, obzirom da su funkcije intenzivne na cijelom području, nije se pokazalo najefikasnije na nekim problemima, posebno nelinearnim analizama, tako da mislim da su atomske funkcije budućnost u primjeni metode R funkcija, tako da se one uvedu u postupak. Dakle, da se iskoriste ona dobra svojstva koja su napravljena kod R funkcija, a da se nadopune sa primjenom finitnih funkcija. Ovdje je jedan takav primjer, jedno trokutasto područje koje je pomoću R funkcija određen je jedan upisani stepenasti poligon i također ovaj opisani poligon. Unutar ta dva plava poligona nalazi se granica područja. I jasno, na granici, na rubu područja moramo zadovoljavati rubne uvjete, bilo Dirihleove ili Neumannove. U ovoj metodologiji nema nikakve bitne razlike. U području se rješava fizika problema bilo kojom poznatom metodom. U točkama upisanog poligona zadovoljava se jednadžba problema, ali se zadovoljavaju i uvjetne jednadžbe rubnih uvjeta. I također na opisanom području, tako da na opisanom području zadovoljavaju se rubni uvjet, a s tim zapravo se zadovoljavaju uvjetne jednadžbe za funkcije koje su na ovom posljednjem prstenu koji je dovoljan za ovo zadano područje. Toliko za sad. Hvala.
Thank you, Professor. So let's go further, and the next presentation is the application of FAB basis functions for modeling of engineering problems. Vedrana Kozulić and Hrvoje Gotovac. Welcome.
Hello, everybody. I will share my screen. Okay, I can start. My name is Vedrana Kozulić, and I will present the use of atomic basis functions in computational modeling of engineering problems by solution structure method. This numerical procedure enables exact treatment of all prescribed boundary conditions at all boundary points, and does not require numerical integration. It combines mesh-free method, known as solution structure method, atomic basis functions, and collocation technique. The original idea of the solution structure method is due to Kantorovich. He proposed to express the solution of a two-dimensional boundary value problem with homogeneous Dirichlet boundary conditions by a formula called solution structure in the form of the product of two functions, where omega is a known function that takes on zero values on the boundary of the domain and is positive in the interior of the domain. And phi is some unknown function that allows to satisfy the differential equation of the problem. Unknown phi is usually represented by a linear combination of basis functions. Generating omega functions over the complex area is proposed by Ukrainian scientist Vladimir Logvinovich Rvachev. He suggested using R functions based on the theory of R functions. The R function method, also known as a solution structure method, has been developed. Rvachev came up with the idea that logic operations of Boolean algebra are applied to the functions. Basic R operations are negation, conjunction, and disjunction. Using these operations, we can determine the function omega over the very complex domains. Then such functions are called R functions. For non-homogeneous conditions, let phi be the extension of the phi 0 inside the domain omega. Then this solution structure satisfies the prescribed boundary condition exactly. In practice, the function phi 0 may be specified in a piecewise fashion with a different value phi I prescribed on each portion of the boundary gamma I. Such individual boundary conditions may be specified into a single global function phi in this manner. General solution structure for mixed boundary conditions can be written in the form that interpolates boundary conditions on gamma 1 and gamma 2 according to Rvachev. Here H is a part of the Robin boundary condition. From the general solution structure, we can derive solutions for all cases of boundary conditions. For H equal 0, Robin boundary condition becomes Neumann. For these mixed boundary conditions, we derive the solution structure for only Neumann boundary conditions with these substitutions. The solution structure can be written in this form. For only Dirichlet boundary conditions, the previously mentioned solution structure is derived. A solution structure can be written in general form. Only the third differential component phi is unknown and can be determined as a linear combination of chosen basis functions. Here, we propose to use FAP basis functions because they are finite functions. They have compact support and good approximation properties. Atomic basis functions also have their roots in Ukraine and have been developed by Rvachev. Atomic functions are infinitely differentiable functions with compact support in numerical modeling. We applied the atomic functions of algebraic type, FAP-N. Index n is the FAP order. Index n denotes the highest degree of the polynomial that can be expressed exactly in the form of linear combination of FAP and basis functions. This figure shows the function FAP4 and its first 5 derivatives. For the FAP basis functions, it is optimal to perform collocation in natural knots, which are the vertices of basis functions. Two basis functions set can be complete. We must keep all basis functions with the vertices outside the domain that have values inside the domain different from 0. And we have to write one conditional equation for each of them. It is only necessary to satisfy the differential equation in collocation points inside the domain. For the coefficients of basis functions with vertices outside the domain, we use the following recursive formulas that represent connections between external and internal coefficients. Here are presented several simple examples of heat transfer problems. Example 1. Consider the floor of height h isolated at one end with internal heating. Mathematically, this problem can be described by differential equation of steady heat transfer with the mixed boundary conditions. For the load function Q, analytical solution of the problem is in this form. Following values are selected. This is comparison of analytical and numerical solutions for different number of collocation points. It can be seen that the largest deviation is at the right side where the Neumann boundary condition is given, but as the number of basis functions increases, the deviation decreases rapidly. Example 2, consider the wall of thickness L, which separates two rooms of different temperatures. This is a non-steady one-dimensional heat transfer problem described by partial differential equation of parabolic type. Alpha denotes thermal diffusivity of the solid body. In this reference, for alpha equal 1, we can find an analytical solution of the problem in an open form. A mathematical model for this problem can be written in this form. The initial condition is the temperature of the wall, while the boundary conditions are temperatures on the wall surfaces. Comparison of analytical and numerical solutions for time step delta t is equal 0.01 is presented on the left side for spatial grid delta x equal 2 and on the right side for double denser grid. In this non-steady problem, sharp changes of the solution function at the edges of the wall are expressed for small value of elapsed time t, and for a small number of basis functions, deviations from the analytical solution occur. However, this deviation is reduced by increasing the number of basis functions. How to increase the value of elapsed time, and as the physical process closer to solution for the steady state, it is the deviation from the analytical solution less and less, and it can be concluded that satisfactory solution is obtained even for a relatively small number of basis functions. This figure shows the function FAP4 for numerical analysis of two-dimensional problems. Now we can solve a Laplace equation with non-homogeneous Dirichlet boundary conditions. This equation models stationary distribution of temperature with the known values of the temperature on the boundary. Let us consider a circular domain with a circular hole in the center. This problem has analytic solution, which can be written in a closed form. The solution of the problem is represented by this solution structure. Phi interpolates the prescribed boundary conditions and is constructed using transfinite interpolation. This figure shows a distribution of temperature from a value 1 on the outer boundary to the value 2 on the inner boundary of the domain. And this figure illustrates dependence of the solution error on the number of basis functions. In this case, we solve the Laplace equation with the Robin boundary conditions. H is a convective coefficient. These are prescribed boundary conditions on the outer and the inner boundary. The numerical solution will be represented by a solution structure in this form. Function psi that interpolates the prescribed boundary conditions is presented in this figure. This is analytic solution of this problem. This graph illustrates convergence of the numerical solution as the number of basis functions increases. It can be noticed that in case of Robin boundary conditions, the convergence rate is lower than in case of Dirichlet boundary conditions. The last examples are solving the torsion problem of a prismatic bar. Here, our function method is applied to the torsion problem for a bar with a cross-section shown in this figure. This is a boundary value problem with Poisson equation and the homogeneous Dirichlet boundary condition. Shear stress components are determined by the stress function U. We know the exact solution for this domain, which is used here for comparison. We represented approximate solution in this form. Function omega is defined by these expressions. For the undetermined function phi, we choose a linear combination of FAP4 basis functions. Uniform grid of collocation points covers the given domain, but does not conform to it. Only points within the domain are collocation points, these red dots. For points outside the domain, these black dots, recursive formulas are written, while the remaining points, these white dots, are not included in the procedure. As we can see, the numerical values obtained with this grid for stress function in the point A and the maximum shear stress are practically the same analytic ones. This figure shows the shearing stresses computed by a solution structure method. In the second example, we consider the practical engineering torsion problem for a bar with a cross-section shown here. Approximate analytic expression for torque for this cross-sectional shape in terms of parameters R, A, and B has been derived in this reference. For this example, the value of the maximum shear stress component predicted by the closed form expression is 18.22, while the computed values converge to the value 18.40. Thus, the deflection runs up to slightly less than 1%. To confirm the obtained numerical solution, we performed the numerical modeling using the finite element method. This figure presents the diagrams of shear stress component in section SS, which were calculated using R function method and the finite element method. And it can be seen that these diagrams coincide excellently. To estimate approximation errors, we consider the same domain for which we know the solution of the Poisson's equation in this form. Figure presents the results in terms of relative solution error in the L2 norm. versus the square root of the total number of basis functions used. The obtained convergence rate is 3.3, while theoretical value for collocation method solving smooth Poisson problems should be 4. But in this case, we have a rough solution consisting of a few singular points. Finally, in conclusion, it can be said that the solution structure method is unique amongst the mesh-free methods because it can be constructed to satisfy all boundary conditions exactly. Because of that, the solution procedure does not require mapping the geometry of the domain. Combination of atomic basis functions and the solution structure method gives numerical solutions that have characteristics of analytical solutions, because solution structure method enables exact treatment of boundary conditions, while atomic basis functions ensure numerical solution with the desired level of accuracy. However, while using this method on one-dimensional examples, we obtained numerical results of excellent accuracy with a small number of basis functions in the area. It should be noted that for two-dimensional problems, the expected level of accuracy and convergence rate on irregular domains was not achieved. We are currently working on developing of a new algorithm to solve the boundary value problem on general domains. The approach combines the collocation method and the atomic basis functions of algebraic type called the FAB functions. All conditional equations related to the boundary of the domain are written at the collocation points on the polygon inscribed in the given domain. It is this blue line. The known value of the boundary condition at the point on the boundary of the domain is satisfied from the collocation point inside the domain in such a way that the Dirichlet or Neumann boundary condition develops into the Taylor series. The method is particularly successful in combination with the Rvachev's theory of R functions that provide a powerful tool for geometry description. Here are some results of a numerical example that demonstrates the efficiency and feasibility of the proposed method. The expected rates of convergence of the numerical solution as well as its derivatives are confirmed. And my time is wasted. Thank you for your attention.
Thank you, Professor. So I suppose we are in time, so we have quite time for the questions. So welcome to ask any question.
Yeah, maybe one comment from my side, Johan Gielis. So yeah, I'll put on my video. Yeah, so anyway, so thank you for your interesting talk. I've also read your paper on the Poisson equation and so on, and torsion. My next talk will also be about different domains, but I would like to see if there's a possibility for collaboration in the future, because we're also working on torsion. So anyway, very interesting talk.
Thank you, Professor Gielis. So any more questions or any comments? Appreciated. Okay, maybe let me ask just a simple question about the last triangulation, let's say. So my question is about how do we triangulate the domain, because we have different shapes inside.
We have a regular grid on 2 dimension, and our boundary is complex or simple, but we have collocation points in vertices of the basis functions in that grid. I have no presentation now. And in that collocation points inside the domain, we written a differential equation. And boundary conditions are satisfied in the collocation points inside the domain with this develops in Taylor series. And in that way, all basis functions that have vertices outside the domain, which have support in the domain, are in the process. All other basis functions on this regular grid are not included in the process. And by R functions, we can define geometry exactly, and we know which collocation points are inside and which are outside. That is the way we are just working on that new algorithm.
Okay. Thank you. Any more question? Professor? Yeah, sure. Sure, Professor. Yeah.
Maybe I've got a problem with the microphone, but you can hear me, yeah?
You're audible, right.
Okay. Vedrana, I would like to ask you a question. Vladimir Logvinovich was my teacher, and I actually spent 10 plus years on the problems which you are solving. And my dissertations was a combination of finite element methods and R functions. So basically, I published the book, which is called Finite Element Methods in Mechanical Engineering, where I'm describing many variants of finite element methods, including integration with the structural method of Rvachev and R functions and different options. But what I found is, for simple problems which you described, it's quite easy to construct the nice solution. It's kind of simple domains, and but if you go to the complex cases like a 2-dimensional, 3-dimensional constructions, this is where nightmare started. So basically, if your omega function, which describes geometry, is very complex, then the derivative of this function will be even more complex. And basically, we are exactly satisfying the boundary condition, but we are significantly worsen differential equation in some cases. So I found it's a kind of very complex problem, and so basically, in my book, I propose different options, and we had multiple discussions with this one problem with Vladimir Logvinovich for many, many years, and not only myself and other people as well. So structural method can be good, and structural method can be not good. All depends on the quality of the so-called quality of the solution. My question is, have you tried to use it for more complex, like a three-dimensional problems, and you know, with complex W function, you know, and where can you stumble with the unresolvable problems where the method simply doesn't work?
We are just on the two-dimensional problems, and I agree that it is very complex to proceed to through a three-dimensional problem, especially the function omega in the method, the structural solution method, and this first part of my presentation is this solution structure method with the construction of omega function. And I agree, and that in the procedure, derivations of omega functions for complex area is very complex, and this is a disadvantage of this method. And we have problems with accuracy and with the convergence rate. So in the last slide of my presentation, this method is not solution structure method. We use only R functions to define geometry.
Okay.
Only for geometry to know which points are inside the domain, which points are out of the domain. And we in procedure, we don't try to find derivations of omega function. We work on different way.
Yeah, I actually come up with the same idea that, you know, omega function can be useful to generate a grid, not to use it inside the structural method, but as a generation of grid, for example, or describing geometry and so on. But structural finite element method, which is I'm describing in my book, it's kind of very, very controversial and still needs to be developed in future, you know. So even it's a good idea, but you know, reality is finite element methods are used everywhere, but and it's massively successful. But when we try to enhance it with the complex procedures, you know, it creates lots of headaches. But anyway, thank you very much for your reply. And I stumbled with the same problem like yourself, and I'm glad this scientific direction still developing. Thank you very much.
Thank you.
Thank you. Any more questions?
Maybe only Oleg to say that also I have a little presentation like second part of our Croatian presentation. Maybe you don't know that. Okay, very shortly before Professor Gielis, I will present second presentation.
That's very good.
Of only to share screen, sorry. Just a moment. sorry, I have some. Okay. Okay, now you see my presentation.
Mhm.
Oleg?
Yes, we see it.
Okay. Yeah. I will now, yes, I agree with Professor Eremenko, because our Croatian school of atomic bases and their functions, we also noticed, of course, a lot of implementation problems with original air function method. Now I will shortly present another option. It is control volume isogeometric analysis with FAP basis functions, because isogeometric analysis developed by Hughes 15 years ago now is very popular methodology. It is based on B-splines, and especially non-uniform B-splines, NURBS, and now it is a very massively developed method. And also it is sometimes called like spline finite element methods. Of course, that FAP basis function, like perfect spline in some sense, is more powerful than splines. And I will show very shortly some our advances last few years in this direction. It is mostly based on our recently published papers a few years ago, especially in International Journal for Numerical Methods in Fluids and in Advances in Water Resources. Our idea to use isogeometric analysis with FAP basis function is multi-resolution description of geometry, material, loading, and of course, a basic numerical solution which we want to solve. This is typical presentation of isogeometric analysis. Of course, it is not the same like finite element, but it is of course more powerful than finite elements, in sense that of course you have transformation from physical mesh to the parameter space or virtual mesh, but now you don't have transformation element by element. Now you have transformation subdomain to subdomain. And also what is very important, spline basis functions, NURBS especially, they describe different geometry shapes in CAD system, in auto industry, in car industry, in aviation industry, and so on and so on. It means that we have transformation the same like in finite elements, but of course now we use B-splines or NURBS basis functions. In this our work, of course, we replace that with FAP basis functions. And we have solution description like in usual linear combination of FAP basis function. We have geometry description like in finite elements using Jacobian and inverse Jacobian, and transformation. And like Professor Eremenko said before, also on the other side, isogeometric analysis has advantages, but also and disadvantages in comparison to the air function method approach. We can describe solution, geometry, but also material like some functions. And what is the basic point of control volume is that we divide our domain into the control volumes, but we use isogeometric analysis for transformation of domain for everything. But in essence, we use, like you said, regular geometry in transformation parameter space, and every point represents one basis function, vertex of basis function, and this rectangle represents that control volume. And we can describe any function. For example, in groundwater fluid mechanics, we describe heterogeneity or long conductivity field. You can see now that we can, because of beautiful multi-scale properties of FAB basis function, we can describe some low conductivity field within many scales. Some very low scales, but after some times we can go to the fine scale as we developed this field. It can be very important for many applicative analysis. Numerical flow solution or some other numerical solution we describe also on control volumes. And as you can see, this is typical typical weak formulation of differential equation. Indeed, we solve these fluxes on these four borders of rectangles, and we also describe Neumann boundary condition in weak sense. Of course, that boundary control volumes with Dirichlet boundary conditions we need to satisfy in this strong way, but also we can use weak form as well. Another advantage of generally FAB basis function and any combination air function or isogeometric is that we can, for example, in fluid mechanics, velocity is derivative of basic numerical solution, but also this velocity is the most important physical variable. And now we can satisfy local and global mass balance property with this control volume algorithm. We can use implies reduction of numerical dispersion. We can use many nice mathematical properties of FAB basis functions. For example, one example from our recent published paper. For example, this is mod flow classical control volume solver in groundwater hydraulics and hydrology, and this is control volume isogeometric approximation of this piecewise constant field. You can see some five transmissivity zones and their very heterogeneous distribution. And for example, for some homogeneous solution, you can see that our solution mod flow is very similar, but for high heterogeneity case, it is not the case, and you can see some sometimes important differences. This is also convergence rates, like Vedrana also presented before for collocation procedure. And you can see that we, for example, for FAB1, we, for any heterogeneity level, we always have convergence rate 2. But you can see on the right side that it is not the case for mod flow and finite element. They lose convergence properties as we increase a heterogeneity level. You can see one realistic case in mild left and right heterogeneity flow case. And of course, again, we study convergence for flow, for basic variable head. And you can see comparison between Galerkin control volume and collocation algorithm. And you can see that Galerkin finite element type of algorithm is always superior. Collocation is very simple, but you can see red curves are usually not so powerful in convergence sense like that. And control volume is something between. You can see for example, from FAB3, that it is very similar like Galerkin case. But on the other side, what is point of control volume for flow dynamics problems, because we have mass conversation, and it is very essential property of this methodology. For velocity, that is derivative of head, it's very important that you can see that control volume are practically the same like Galerkin, but with smaller computational price and with more physical basis. You can see also computational efficiency for low level of FAB basis function, for example, 2. You can see that Galerkin is still the most powerful, but if you go to the high order methodologies with FAB4, then control volume becomes superior. For example, flow in irregular geometry, you can see that then we can also describe our solution. But for example, if you have some discontinuity, like in this this corner A, unfortunately, we have deflection of convergence rate. That is the reason why recently we developed a new form of FAB basis functions in sense of hierarchical FAB basis functions, and we succeeded to show that it is much more efficient than hierarchical spline basis functions, and it is building block for our adaptive methodology. And these formulas is essence of that methodology, because we can show or describe one FAB basis function with linear combination of FAB basis function with higher order and higher frequency or smaller compact support. You can see that of the lower picture. This is FAB1, and this is linear combination of FAB basis function of FAB2 with smaller compact supports, and this is exact relationship. This relationship, which we knew for 20 years ago or more, now we finally use that in sense of adaptive control volume isogeometric analysis. For example, this is one presentation of 1D solution with black FAB1 solution and red FAB2 basis functions. It means that we can combine now any combination of different order of FAB basis function, and absolutely that we get new basis, new vector space with much powerful properties, as we will see later. This is 2D, the same like 1D, but now you can see blue vertices FAB1 and green vertices FAB2, and red rectangles are different control volumes on first and second level. You can see on the both side also FAB and FAB2 basis function in each direction. You can see again a very interesting combination of different orders and frequencies of basis functions. And last example, only to illustrate this advances. This is wave front well problem, classical Poisson problem. You can see left analytical solution. This is error between analytical and numerical solution. You can see very small differences. And here is adaptive grid, which includes evidently FAB1, FAB2, FAB3, FAB4, FAB5, and FAB6 basis function together, describing this very strong front in this well groundwater problem. You can see also convergence order. This is like before. This is uniform FAB grids, and they have, like splines, they have polynomial orders. But now we have black line. We have much more better convergence properties, because adaptive control volume formulation gives spectral convergence. It means that now convergence order is greater than polynomial order convergence rate, because this is more than n+1 when where n is the FAB order. Conclusions, as we can see, our recently published papers show application of control volume isogeometric analysis, combining good properties of collocation and Galerkin robustness. Velocity field is continuous with optimal convergence rate, and very important that this procedure enables development of hierarchical FAB basis function and adaptive solution procedure. Our ongoing and future work includes development of parallel adaptive 3D codes for solving very powerful realistic problems. And of course, this adaptive solution with hierarchical fab basis function can be incorporated in previously presented air function method, not only in isogeometric analysis framework. Thank you very much.
Thank you.
Thank you, Professor. Sorry. Okay.
Can I please?
Let me ask you.
Yeah, please mute sound of some presenters, of some people who watch us.
Can you hear me?
Yeah.
Yes.
I would like to comment on the presentation. Basically, I like the idea of the adaptive and hierarchical approach, which is much more better than using standard fab functions. And I understand why. Let's talk about, for example, finite element methods. Finite element methods, it's a universal. It can basically numerically solve very complex problems, and basically it's widely used. But there is a problem with finite element methods. It is always approximation of the solution. It's not exact finding of the solution, but approximation. For example, if we are using quadratic basis functions, by the theorem of strength fix, we can only exactly represent parabolas. That's it. If, for example, our solution is cubic parabola, with the final element method, you will never exactly reproduce cubic parabola. So the same situation here. If you are using, for example, fab2 basis functions, you are limiting yourself only on the certain type of solutions, which is kind of close to parabolic. But if our function is much more complex, fab2 will not give you ultimate solution, which is close to exact. But if you are combining, fab2, fab3, fab4, fab8, fab10, and you can create adaptive algorithm, it will be much more better convergence. And this is what you see in your, last slides, So the rate of convergence much better. This is because with atomic functions, by definition of atomic functions, you can exactly represent polynomial of any order. For example, if our solution is polynomial of 10th order with enough atomic functions, it will be exactly convergent to this one. This is the beauty of the atomic functions. It can exactly represent polynomial of any order. Finite element method cannot do it. It's always approximation. And this is very important. And I basically praise you for this direction. It's very interesting.
Thank you, Professor. I absolutely agree with you. And also, after many years, realized that if we use uniform grid and one order of fab basis function, we are better than B-splines, but not too much.
That's right.
We have the same order of convergence and everything. And
that's right.
This is a very powerful illustration how atomic basis function can be better. Unfortunately, atomic basis function require much more knowledge than low order finite elements, control volume, and similar typical methods. And absolutely that we need to push much more effort to development of some new advances with atomic basis function, because unfortunately it is much more difficult than with classical numerical methods.
Yeah, I agree with you.
Yeah. Thank you.
Thank you, Professor. So we are a little out of time. Let's go on further and move to the next presentation by Professor Gielis. Your microphone is mute. Professor Gielis, let me ask you to switch your microphone on because it is mute now.
Yeah, okay, good.
Thank you.
So you see my presentation now?
Yeah,
Oleg?
right.
Okay,
right.
good.
Yes.
Yeah, thanks for the opportunity to present our work. It was born out of, let's say, a geometrical approach of describing nature and describing natural shapes on a very broad level. So first of all, there's a little overview. I had to make a selection of the works that have been done in the past. I will show how we got to what is called the superformula and Gielis transformations. I will point out that this origin is very closely related to our functions. And then I will talk about generalized trigonometric functions and so on. Our work is a lot of exploration, but also verification. I will show you. It's also about unification and inspiration. And of course, I don't do that alone. So over the years, I've built very close relationships with mathematicians and engineers. Professor Ricci, who is also on the call, is the second from the right. Diego Caratelli, will also meet him, and Johan Fougeral are in the middle and to the left. There's also a large part of the work has been done in Nanjing Forestry University with Pei Jiangxi about verifying the equations in nature. And he has a whole team of people going into the forest to collect all kinds of materials. Johan, I met Johan, and that was one of my first connections with our functions. Actually, he did his thesis on combining my work with Rvachev's work in 2004. Unfortunately, for science, he moved out and he started his own restaurant. He moved out of academia. But throughout the years, we've been working together on image recognition and we're further into investigations. But he told me, still, I'm seeing super shapes every day when I prepare my meals in the restaurant, he said. So from super ellipses to superformula, my work is actually a geometrization of the shapes of natural organisms, providing a descriptive basis for larger geometrical theory of shape morphogenesis. But it starts from Lamé's work. And Gabriel Lamé lived from 1795 till 1870. And he was also for a while in St. Petersburg before moving back to École Polytechnique. But what was important was that he dreamt of a science rationnelle unique, where you have a best possible coordinate system adapted to a physical system and then solve boundary value problems. But when he was young, he wrote a book about the generalization of the circle into supercircles on the lower right. And these are called now Lamé curves. The first encounter in Lamé curves and botany, I'm a botanist, by the way, my background is botany, was actually when I looked at the shape of square bamboos. Mostly bamboos are cylindrical, but some really have a super circular shape described by Lamé's equation. And on the right, you see star fruit. So you see some fruits and some flowers also having the same very shape. And wherever we look in nature, we find very similar shapes. I have to move to the next level. But we could describe with these Lamé curves, we could describe anything squarish and super elliptical, but there are many other symmetries in fluid mechanics, in flowers, in diatoms. Just for the record, you see now the slide, what about other symmetries, right? Oleg?
Sorry?
You see the slide now, what about other symmetries, huh? Right?
Definitely, absolutely.
Okay, good. Yeah, just to make sure. So I published my findings in 2003 in the American Journal of Botany. It was about the generic geometric transformation unifying a wide range of natural and abstract shapes. And that generated a lot of attention, and it also, we could develop many of the collaborations that led to the results that I show. So how did we do that? So first of all, you have in the middle, you have the supercircle, the Lamé curves. And then we transformed it with a student of mine back in 1997 or so into polar coordinates. And then I did a trick which turned out to be very useful. If you add m divided by 4, you can divide the plane into more sectors. And doing that, you can also apply it as a transformation onto other functions. Here are some examples. For example, if you have m is 4, you have all the Lamé curves, but if you fill in 3 or 4 or 5, you can get starfish. And you can apply it also to logarithmic spirals, Archimedean spirals, or to trigonometric functions, either flowers, I'm a botanist, or the wave-like functions. And again, it's an equality, but if you define an inequality, you can define anything inside and outside as well. The first part of my discussion on exploration was how widely is it applicable? Does it only apply to square bamboos or also more? And also with Nanjing Forestry University, it's not, we did it from an analogy to testing on real life specimen. So back in 2003, 2004, mathematicians and geometers really realized that this was a way of describing very complex natural shapes as well. Enormous diversity, and they started to call it Gielis transformations. And then with the Nanjing Forestry University team, we started to look at bamboo leaves, tree rings, bamboo culms. Number 2 with the red arrows is actually the square bamboo. And we needed, with this formula, in a simplified form, we needed only one equation with 2 numbers, one for shape and one for size. And we could identify we tested 10,000 bamboo leaves, we tested 20,000 leaf tree rings, and so on and so forth. So it was all done on a statistical level. But also for leaves, for example, you could identify in the middle, you see a lot of leaves that you can do with this one formula. And we tested it on maybe 5,000 other leaves, elliptical-like leaves. And it always works, even if the fit is not really very beautiful, like in panel C on the lower right. But then again, these 2 numbers estimate the area correctly. And the area is the most important aspect for leaves, of course. We also tested it on starfish. We tested it on diatoms. We tested it on fruits for a triangular case on fruits of Coloreteria. So botany and biology, it works there pretty well. So, but one of the major developments was, it was back in 1993 that and it doesn't move here. Yeah, it also works, for example, on eggs. Last summer, there was a lot of interest in a universal equation for eggs. It was published in a journal in the US, but it was called the Narushin-Romanov-Griffin equation. But then again, if we tested it with our equation with just 2 parameters or 3 parameters, we could even do better than their equation. So this is a paper which we hope to have published in the next period. In 2020, we went back to the original idea. So the team of Nanjing harvested 30 columns of a square bamboo, Hymenobambusa utilis, and they cut just 750 sections and made up, some were broken, but then you had an inner shape and an outer shape. And we found that all 1436 shapes fit very, very well with the super ellipse. Sometimes it was also a sub ellipse, and I'll show you what was very important. Of course, we had to introduce one deformation parameter for some shear things. What was very important to find, and a major finding, which we believe will be of major importance, is that if we look at the exponent values of the outer rings mainly, we see super ellipses with exponents larger than 2 and smaller than 2, but we don't see ellipses and we don't see circles. The same for the inner ring, although it's less pronounced there. Now you might say, well, of course it's a square bamboo, you do not expect that. But then we went back also to the original tree rings that I showed earlier. And in this 5,000 or so tree rings, there was not a single or just a few circles to be found. Although these tree rings look circular, they're actually Lamé curves. And that's a very important finding because most of the geometrical apparatus is based on circles. So, but nature does it differently. Bamboo culms, tree rings, and so on. What was also important from a geometrical point of view is that we have now the circle and the square, or circle and spiral as two basic functions in nature, and there's a whole theory behind this. But now with one extra transformation, rho phi in this case, we can describe so many philotactic or so many mollusk shapes. We can describe starfish. And again, this could be, if we look at the starfish could be different species. They could be different evolutionary forms. They could be a development from one small thing to a larger specimen. So it's an evolution in time of whatever sort. But this is now all possible with one transformation. And one of the, as I said, inspiration and exploration. So now with the Indian astronomer, we're exploring also galaxy shapes. You see also, typically we think of elliptic galaxies or spiral galaxies, but you see that even in the elliptic galaxies, you have boxy and disky and pointy galaxies, and they make up about these non-elliptical, they make up about 25% of the elliptic galaxies. And even in the spiral galaxies, you have shapes that we also are studying. For example, on the right, you see a remarkable rectangular galaxy, LEDA, which was published in 2012. So it works at all levels, and our, let's say, verification is trying to see how many of that and if our method fits well. We also have applied it to describing fluids, patterns in viscous fluids, for example, which can form, depending on the circumstances, can form triangles or two angles. And also in silver halide crystals or many crystals, you can describe different shapes by one formula. Even if these shapes have a short, long sides. The interesting thing is that actually Lamé originally discovered or used these functions to describe crystals. So we have shape-specific coordinates for all creatures, great and small, all to be verified, of course, but we have for enzymes, DNA, or for square bacteria in the middle left, or for galaxies, or for snowflakes on the middle right, or yesterday, so triangular coiling of mollusks, or space-times and Minkowski cones, light cones with a star-shaped cross-section. What was interesting to find is that, as I said, we use mostly circles and straight lines to describe curvedness. And, but we find in more than 40,000 specimens that we don't find any shape, we don't find any circles, only supershape. So what we are trying to do now is build a more general, let's say, language based not only on circles, but also on supercircles. The original paper has been cited more than 560 times now, so it has been applied in almost every corner of science and technology, not all corners, but for example, in antenna, there are now more in the antenna field, more than 80 papers published using the formula to describe new shapes of antennas, or in laser. It has also been used in education. There's books in Croatia, there's in Italy. Many teachers also were interested in this. So my daily occupation, as I said, I'm a botanist, but with Diego Caratelli in the middle, he was a mathematician and an antenna engineer. We founded the antenna company, and we have now 35 plus people, and many patents and many products. And this is a slide showing that we use it in very different ways. We use it not only to design new antennas and antenna systems, but also for ultra-fast computations and multi-objective optimization. So here are some examples of antennas and systems in wireless modems and routers, but also for filter design or for metamaterials. This is something that opens windows. You don't only have to choose between a circle and a square, you have all kinds of transitional forms. Now, I showed you about the verification in nature and in technology, but in geometry, it's a bit different because there you can really prove things. I will show just a few things, which I think allows us to look differently at things. If we start with the rules of arithmetic, for example, what we typically see, and on the lower right you see the Galston board, and you can show there is to look at a binomial distribution based on Pascal's triangle. What is important here is to see, well, actually, if you want to throw up, toss 1,000 times a coin, let's say tossing 1,000 heads or 1,000 tails is extremely unlikely. It can safely be neglected. So much of science developed mainly focusing on the center of that Pascal's triangle. But if we look at the same rules of arithmetic in a different reading and use only these pure numbers on both sides and just forget about all the rest in the middle, then we have a kind of modular arithmetic, which is well known in arithmetic. But then the trick is, if we add them, if we have two sides and we do an addition, we have everything super circles, we have everything super ellipses, we have Minkowski distance. If we multiply them, for example, y to the m is x to the m, then we have everything which is power laws or power functions. And on the right, you see power, let's say super parabolas from I is x squared to I is x to the 1/2. So within this, thinking about it differently with a different reading, same rules of arithmetic, we can study nature in a completely different way. What is also important here is that we call this equation Pythagorean compact. So because if you choose m is 4, then we have cosine to the n plus sine to the n. And if we choose 2, we have the circle. So within the same formalism of Pythagorean theorem, we have both the Cartesian and both the equation. And even if we choose something else than cosine m divided by 4, we could have a cosine of some other function. It's still Pythagorean compact. Another thing which is, so we choose, for example, for botany, we choose different exponents and m divided by 4, but you can put many other let's say functions in there and generating a lot of other shapes, still Pythagorean compact. What is also important is thinking about oligomals. So if you have x to the n plus y to the n, you have only two variables to some exponent. And that Vladimir Arnold and Olga Oleinik described this as topological complexity of an object is not the degree of the equation. That's could be of arbitrarily large degree, but you have to have a restricted number of monomials. So in this case, if we look back also, if you look back, then you see that this is also topologically simple in the sense of Arnold and Oleinik. So going back, yeah, so another thing is, how does it fit into the whole of geometry? Go back. And actually, Xingxing Chern was one of the most important geometers in the second half of the 20th century. And if we look at the development, so this we are talking here about the framework of Finster geometry, Finster-Minkowski geometry, and submanifold theory. In the 20th century, there was mainly Riemannian geometry, but Finster geometry is much more general. It does not take care, it does not really restrict it to the quadratic equation. Another thing for the development in the future is that an extension of the idea of manifold was also advocated by Professor Chern. I will show a few examples. When we think about Minkowski distances, these are very well known. So it's a kind of geometry in which lengths are measured differently in different directions. The city block, the Euclidean max metric. And you can also teach that to children. This is from 6 to 7 year old children in the 1960s. It's one of the images from the book of Petar Mladinic on the geometry of nature, published in Croatian and English. But you could also take the same thing and think about Minkowski distributions. Now, if you go to the infinitesimal, then you arrive at Finstler geometry. Finstler geometry was originally in the it's called Riemann-Finstler geometry because it was originally in Riemann's Habilitationsschrift using some fourth power. But Peter Antonelli, one of the foremost Finstler people, said, well, we need also not only the theory, which is pretty complicated of Finstler geometry, but we also need examples in nature to study it. And he gave an example also into ecology. And now, as I have shown, we have many, many useful examples for a general way of thinking about Finstler Riemann-Minkowski geometry. So that's the general work. When we think about generalization of the idea of manifolds, we can, with this formula, we can also define regular polygons or self-intersecting polygons. And if we look, for example, pictures taken from a book from Professor Gianni from Tbilisi, we see that you can define certain geometric shapes, but there are restrictions. And on the right, you see an image that we made also with our formula. Another way is that we can describe very complex domains by combining, for example, triangles defined by our equations with our functions. So there are Cox snowflakes. This is not a fractal, it's just an iterative procedure. The interesting thing is if we go to a third dimension, then we define something like two sections. So there's two perpendicular sections of a shape. A sphere in two, if you cut it like this and if you cut it like this, you have two circles. And that's all you need. One is the, let's say our row one is then the shape of the cross section. Row two is the path along which this cross section is drawn or dragged. And so you can define, for example, a pyramid as a triangle in one section and a square in the other. And that's all you need. So even if the path becomes wider than for example, the cross sections, you get into tori and square tori and spindle tori. It's actually a continuous transformation, or as you can see on the lower right, going from a sphere to square tori in just by adding a longer radius. What is interesting then is if you think about shapes like we see here, are they complex or are they simple? In my view, they are simple because they're just another set of 6 or so numbers, different from a sphere, but only 6 or so numbers. And so it's a completely new way of thinking about shapes. We also built back in the days, 10 years ago, 15 years ago, a kind of modeler, CAD modeler. And just to show that geometrical information based on just a few numbers of three-dimensional shapes creates extremely small file sizes. And you're not restricted to toroidal systems or spherical systems. You can also think about cylindrical combination, cylindrical or canal surfaces. And this is research that we do with Professor Ricci and Professor Tafkelidze in Tbilisi, generalized generalized Möbius listing bodies. And for example, on the lower right, you see something which this equation, this analytical equation, could also have a time component. So what you see here on the lower right is not a movement, but it's a peristaltic movement. So the cross sections are growing smaller and fatter. That's the movement that is shown here. So this falls out of the scope of this talk, but when we talk about these generalized Möbius listing bodies, we can apply it in let's say in physics, we can apply it in biology, but that's for, let's say, the next decade. What is most important is that it's a general method for fiber bundles or for tangent spaces. Now, the second part is that Lamé curves and Rvachev functions form a very natural alliance. I've made a table here, and on the right you see the RP functions, and there you see for Y3, for example, intersections and the unions, you see a plus or a minus, some distance defined by a super ellipse or a Lamé curve. And also the RM functions also are something like that in disguise. For example, the m divided by 2 exponent is also Lamé-like. So there's a very natural exponent. And that's what was recognized also by Johan Gielis in his thesis in 2004. So he built a complete modular constructive solid geometry, combining these super shapes and combining our functions. And so he did a lot of work on it, lots of publications. And there's full reference sections at the end of my talk, at the end of the presentation, which I will share. And you can define even very complex domains in very simple ways. One of the things which were very interesting in the collaboration with Johan was looking at self-intersecting shapes. If you have, for example, an 8/3 polygon, you have 8 angles in 3 rotations. But then you define also very different zones. And by using our functions, by using differences, we could really define any zone that we saw in these self-intersecting shapes. And we use it in a lot of ways, also in the generalized Möbius listing. But for me, at that time, 10 years ago, it was an eye-opener, because these zones could be zones of differential gene expression. For example, in flowers on the lower right, you see the development of petals, you see the development of stamens, all different sectors. And they all have some kind of spiral phyllotaxy. Also something that caught my interest. But I'll show later that we also played around not only with intersections and unions, but if you add some factor t, you can have many intersections between intersection and union. You can even go beyond union, and that's something not published yet, but it's something, as I said, lots of what we do is exploration, and it's also doing these things is a lot of fun. So regarding our functions, we are building using the original mesh-free superformula modeler, and we'll try to develop it further also for virtual reality and games. And with Revas, Gregoli, and Tbilisi, we're looking at 3 or more valued logics, looking at this. Now, flowers and wave, that's another very natural alliance. I'm a botanist, as I said, flowers on the left, waves on the right, but they have the same, very same, let's say, background. Now, as you see in the scheme, we went from Lamé's curves to a polar representation, and then we went to superformula and Gielis transformation, but there was a big gap. So how do we go back? How do we go from polar to Cartesian? So there's a gap. And this was, again, with Professor Ricci. Originally, my botanical inspiration to m divided by 4 was with Rodinea curves, later also with Chebyshev polynomials. But then it turned out to be that if we use this, if we use Chebyshev's, then we can rewrite the superformula in Chebyshev polynomials. Also going back to the supercircle in special case of this. And that brings out a very close connection between these things. And later also, Professor Ricci defined non-integer, in this case, half Chebyshev polynomials. Sorry, I'm going a bit further, a bit fast. But then we also have the shapes, the equation, my equation describing all these flowers on the top can be described as pseudo-Chebyshev functions. Now, in a more general sense, we also started to look at trigonometric functions which are associated with super ellipses or super shapes in general. And you see that the circular classical trigonometric functions is also only one special case in this case. But what is interesting is if we have, let's say, cosines and sines defined on a supercircle, and we raise them to the same power, then we can prove that every supercircle or every Lamé curve has their own Pythagorean theorem. It always adds up to 1. And this opens, these trigonometric functions open a lot of other possible possibilities. And you can define all kinds of weird shapes or wavelets in a very analytical way. We can also define a kind of more generalized Fourier series. For example, if you, in each term, you apply a kind of, let's say, special shape, you can, in just a few terms, you can also define very weird shapes. Actually, if you look at this generalized Fourier equation or formula, then all the supershapes that I showed before are only defined by the rho 0 and A0 function. Now, this inspired again Professor Ricci to look at the trigonometry on the diamond. And here are some examples, and it turned out to be, with hindsight always, it turned out to be very efficient if you use arcsine functions. And then you can turn, let's say, sines and cosines into straight lines, to put it this way. You can make additions, but Professor Ricci also proved that you can do relevant de Fourier expansions with this. Looking at the lower left, you see Lissajous figures, and there's the classical Lissajous figures are the rounded ones, but you can turn them in really square patterns. And again, possible applications can then be in the representation of piecewise linear functions in a simpler way as compared to ordinary Fourier analysis. For example, seismic data. On the lower right, you see already a paper from 2004 in which they used my equation also to study seismic rays into Finster geometric set work of seismic patterns. So in the first part, I showed that we find it everywhere in tree rings and in starfish and so on, but that takes us to the next question. What about waves in nature and natural sounds? Might they also be superelliptical? So this is an example of somebody who made a synthesizer also using some knobs for super shapes. But if you look at these panels, you see, let's say, super ellipses and special super shapes, the associated trigonometric functions on the right, and then a Fourier spectrum, right? And for example, this, oh, sorry, this should be, here you hear different sounds generated by different, and in many ways we could hear a kind of polyphonic sound. Yeah? So playing with the geometry generates a lot of new sounds that have never existed. And there you see a lot of possibilities, which we call rational Gielis curve, closely allied again to Chebyshev and so on. So the research question, if we can describe natural shapes using supercircles and so on and so forth, we find no circles. Could we not expect that, for example, natural science also have kind of Lamé signatures, superelliptic rather than circles? So our general idea is the Fourier spectra seem very natural, but it's only natural in the sense that we look at it with our circular glasses, where one frequency is one pure sound. But like in the case of shapes, maybe our Lamé glasses might give very different results. Again, if we can define a trigonometry based on the shape itself, then what we see as a multi-frequency spectrum in a classical Fourier might be a very pure sound connected to a very pure shape. For example, that's exploration, where we don't know yet. But for example, the sound of a whale might be a pure sound in whale language. Again, the inspiration is thinking very differently about things. Now, the final part of my talk is that my paper also inspired mathematicians, in particular also Professor Ricci, to use classical methods for solving boundary value problems on normal polar domains using the Fourier projection method. And this comes back to the original idea of Gabriel Lamé, so a kind of unifying science with the best possible coordinate systems adapted to the shape and then solve the boundary value problems. So, and with the coordinate systems adapted to the shape, this can be done using the classical Fourier projection method. Again, in the list of references, there are a number of references, but it is also aligned to the original proposal by Professor Kantorovich. So the idea that Professor Ricci with Paolo Natalini and Diego Caratelli, and that's how we met and eventually started Antenna Company, was to generalize the Laplacian operator for stretch polar coordinates, not for the classical fixed, let's say fixed radius, but for in a general way. You can recover the classical Laplacian operator in polar coordinates by setting it to 1. But then it became possible for very different boundary value problems and different conditions. It became possible to express it in a Fourier series, the coefficients being determined by infinite linear system depending on the boundary data. And on the blue image on the upper is actually something like a 1 angle. So 1, if M is 1, you can have a pointed tear-like structure. You see something, the bluish one on the right is what I showed before in the generalization of manifold idea. But you can also do it, let's say, the wave equation on starfish-like domains, but you can also do this in 3 dimensions. What was interesting also is that the solutions are based on the classical Fourier projection method, and it's very general. It's not only my shapes were the inspiration for Professor Ricci, but it's not restricted to my shapes, of course. Their original publication was, for example, also on Riemann surfaces. And again, in general, and we've seen in the previous presentations, let's say, these graphs for errors. And in this case also, and as shown in many publications, the expansion order of these Fouriers is pretty small. There will be a book by Athena Publishing. It will be out in, I hope, 2 weeks or so, in which we combine the natural shapes and the idea of Chebyshev and these mathematical physics methods. And it's a joint work with Professor Ricci and myself. It's called From Pythagoras to Fourier and From Geometry to Nature. And to finalize my talk, I will show a few slides on flowers. I call it conic sections at the core once more before, but also flowers are very crucial to our understanding of nature. So in this case, it's a group of flowers, Asclepiads, which are extremely beautiful. They're very mathematical if you look at their perfect shapes, almost perfect shapes, but they also have special way of attracting pollinators. For example, they smell like urine or they smell like feces and something, and so they attract flies for their pollination. It's an extremely interesting group of plants to be studied. And back in the day, I was so first of all, maybe this slide. So you have the original where I showed where you have the connection between pseudo-Chebyshev polynomials. These were what we call chorypetalous flowers. Chorypetalous means that you have all the petals are separated. Yeah, and actually what we have here is a cosine m divided by theta, describing the pentagonal. If you have 5/2, you have pentagons. And they are forced with the multiplication, with the transformation, they are forced to grow into a kind of polygon. That's how they got these shapes. But you also have a large group in flowers which are sympatalous. So their petals are fused. If you go back to the previous slide, we can see that the petals are fused here and not separate. So you have a kind of, instead of, we can model this not using a product multiplication, but a weighted arithmetic mean, which is the equation on the right. So you have a developable function which wants to grow, and the blue one in the lower panel, and you have a constraining function, so like the pentagon around the sun, and the weighted arithmetic mean gives you the red curves or the curve on the right, which we find really in natural shape. So again, here we play with just the rules of multiplication and additions to describe this. But this brings me back to one of the first encounters with our functions. And that was when I was presenting our work, superquadrics with rational and irrational symmetries, at the ACM Symposium on Solid Modeling in Seattle in 2004. And there I met Professor Vadim Shapiro, who had already been working a lot with R functions, and he introduced me to R functions. And there you see the first experiments dating back to 2006, 2007 of looking at typical vibration phenomena in such shapes with sympatalous flowers. Maybe there could be a connection I want to understand. And these experiments were run by Igor Tsukhanov using the scan and solve modeler, also mesh-free modeler developed at the University of Wisconsin. And many of you will know the name of Vadim Shapiro, but he also recorded lectures of Professor Rvachev when he was giving talks at Wisconsin University. And these videos are available or made available by Oleg on YouTube. But then later, with the method that Professor Ricci and Diego Caratelli developed, we found that it was also possible not as a vibration problem in scan and solve, but also as a more general way of looking at things as a boundary value problem. And you see that there's a natural tendency of some curvature upward of these things. And actually, that's what we also observe in flowers like the ones I showed before. So the way they open their petals or nectar discs on the right, in the middle, you also see the very same structures. So we see a lot of convergences between natural shapes and the way they behave, and generalized geometric description and really new methods of new ways of looking at things. And what is important also is that what is then the bigger picture? And I think in my way, what we see so far is that we can extend the toolbox of Euclidean geometry with our transformations. If we do that, and we don't need really new maths is needed, so new applications of existing math, just a new set of glasses and lenses to look at nature. And why Euclidean geometry? Here I have two eminent geometers from the 20th century. So René Thom said, classical Euclidean geometry can be considered as magic. Only points and lines are enough to have a pure formal language of geometry, describing adequately the reality of space. In this sense, geometry is successful magic. And also the very famous Russian geometer Alexandrov said, retreat to Euclid. We have to think back in the way Euclid approached things. So that's why we think so far we can just take Euclidean geometry with extra transformations and go back to the original one. This is the last slide. So we have now a unifying geometrical strategy for uniform description of flowers, snowflakes, galaxies, soap films, and so on. And we couple this to natural curvature conditions. This is a kind of geometrical way of talking about boundary value problems. And so minimal surfaces, Willmore conditions, curvatures of space-time. That's the way we are approaching the things now, when we can do it as a kind of generalization of the circle, generalization of the sphere, or generalization of cylinders, generalized Möbius listing bodies that we do. Then again, so it has been published in a range of papers, in a range of books. Some of them are forthcoming. We also have Growth and Form, which is a journal that we publish. It will be just in a few weeks. We publish interesting papers describing the relation between growth and form. Also, our results have been, presented at many international math meetings. These are a list by myself, but also by Professor Tafkalize, by Professor Diego Caratelli, and by Professor Ricci in various occasions. And then there's a list of references that you can consult. All the papers are available on my ResearchGate page, and you can always write me to ask questions. So thanks for your attention. So
thank you, Professor Gielis. So Any questions?
I have a very simple question.
Yeah, welcome.
Can the counters obtained with super formula be self-intersected or not?
Yes, yeah. We have the self-intersecting shapes. If you have m, you have this factor m divided by 4. If you say in 5 divided by 4, then you divide the let's say the plane into 5 sections of 72 degrees instead of 4 sections of 90 degrees. It's as simple as that. If you fill in 5/2 for m, for example, then you have 5 angles in 2 rotations. You have 5 angles like a pentagram. You have to go around 2 times to close. What I showed in the flowers and the self-intersecting section was where this m is actually a rational number. Hello, Paolo. So, hello, gentlemen. So yes, there is a lot of possibilities. So it's a continuous transformation. M is normally a discrete number, so 4 or 5, but you can use it as a real transformation over the reals. The exponents can be real numbers. And again, what I showed is an overview. There's a lot of research being done. It's exploration, it's having fun, it's giving results both in science as a scientific method, but also in a pure mathematical sense.
Thank you very much.
Thank you.
Thank you. So any more questions?
Yes, Oleg. Yeah, thanks, Professor Gielis, to very interesting presentation. I have one comment and also one question. My comment is that is of course this is very interesting and powerful. But my comment is also related to the boundary value problems and realistic application. In what sense? For example, this isogeometric analysis is very popular. Why? Because they show that can connect geometry description by splines and CAD industry with some classical solvers like finite elements, with also splines, which is high order, and so on and so on. And that is the reason why they are so popular. And for example, if I want to connect our presentation and your presentation, then your geometry description is very powerful, but we need to comment relation with CAD industry, because CAD industry is related to the softwares, to realistic life and so on. And after that, we need to make relation between how we can solve boundary value problems, for example, with atomic basis functions, and for example, with basic idea that we solve in some regular mesh, in sense that your geometry description is embedded to that mesh, and that we know only that our basis function is outside or inside your geometry description. And okay, now it's not so, of course, not so easy to recapitulate all possible possibilities and ideas, but maybe you can answer and comment this.
Yeah, just a short comment. I thank you for this question, because my participation in this workshop is really to see if there are connections possible. As I said, in the second slide, I showed a lot of relationships and people that help building these foundations. So we're always welcome to reach out to other possibilities. And I said Lamé and Rvachev functions are very closely related, and there will be connections between up functions and the generalized trigonometric functions in some way. We just have to explore it. As for the other part of your question, so back in 2004 with our CAD modeler, we already spoke to the big ones. But and Vadim Shapiro also acknowledges he has built a full mesh-free modeler, and it's very difficult for him to get inside the PTC, inside and so on and so forth. It's a very conservative thing. So we we really hit our heads against the wall, even with Johan Fougerol's modeler. They were not interested because how many users do you have, they say. So luckily, I met with Professor Ricci and Diego Caratelli. At a certain point, it's a very interesting story, but at a certain point, I saw Professor Ricci and Professor Natalini had already published a number of papers. And then there was a new author, which was Diego Caratelli. And I live in Belgium, and he lives, at that time, he was in Delft, I could see, at the antenna department. So I called him up. And I said, Dr. Caratelli, yeah, I saw your name on a paper. Could you help me explain what this means and so on? And then he said, well, I also develop antennas with your formula. So that's how we could really, but now we have 35 people and we do make the best antennas in the world and all that, but you really need the right people and you need the right investment, and you read, if you even, and we can talk about this later, but if you go with your new method, if you try to convince the PCTs or the other big guys of the world, that's a hard fight, I can tell you. So, but it's an interesting way, but we keep on pushing anyway. We keep on pushing. As for the third part of your question, complex domains, that's where I see also a value for say R functions, the combination R functions, and maybe also the multidimensional case is quite unexplored, or not explored at all, just one case, and also using multi-valued logic, three-valued logic, that's what we're exploring. So there's many possibilities that we can see. So if you look to three-valued logic, you're looking at fuzzy logic, for example. So this kind of thing. So we keep on building, and I have a lot of good friends that enjoy having fun, and we publish a lot. So, but that's part of the game. You have to push for 10, 20, 30 years until somebody picks it up. That's if you do mathematics, it's a long haul. So for the long haul.
Yeah, thank you. Of course, we can talk a lot about these things, but okay, some interesting remarks.
Yeah, as I said, I wrote to you before. Petar Mladinic in Gymnasium 5 wrote a book about this. He lives near Split, so he has invited me to Split. So
hey, why not?
Maybe
we are open for collaboration and spreading ideas about.
Yeah, I have a lot of. There are a lot of excellent mathematicians in Italy too, and that's not so far from Split, I think. So good. Paolo, do you want to add something? Because let's say the method which was developed mostly by you for boundary value problems.
Yes, and of course we are usually absolutely that we are not a specialist in geometry modeling, but without geometry you cannot model realistic.
Absolutely. And a final remark, because we're running out of time. Just a final remark. Actually, as I understand it, again, I'm a botanist. That's always my excuse if I say wrong things in maths. But so the original idea for Fourier was basically on a circular domain of the heat. But when it went to squares and triangles, that was done by Lamé and Mathieu. But after that, the whole development of finite elements was because they could not go further than that. Yes, that's in my opinion, the origin of finite elements, to do it in a different way. Now, Professor Ricci's method and other methods by Professor Rvachev allow us to do it in a more geometrical way and do it in a pure way.
Yeah, okay. Thank you for now.
Thanks.
Can I comment as well? Hello, Rick. Can I comment?
Sure. Yeah.
Thank you, Johan, for excellent presentation. I've got few kind of comments and ideas maybe to discuss. First of all, say hello to Igor Sukhanov. I used to drink beer with him, you know. He was working with Rvachev in his department in Ukraine, and we've been kind of comrades with him, you know. So I know Igor, and he went to US later on, so I know his works. Regarding your presentation, first of all, I've got a piece of good news for you. I had a look at your super formula, and it looks for me that super formula is analytic. There is a definition of analytic function. In analytic function, it's a function which is described by converging Taylor series. So you can basically, for example, sine function. We can have a Taylor series for sine functions. Everyone knows, exponent, square root, and so on. So basically, your super formula includes analytical functions. It includes sinus, cosinus. It includes square root. It includes also inversion functions and so on. So it's and here is the idea. Any analytical function can be represented by atomic functions. So basically, if you use enough atomic functions, any analytical functions will be convergent to the. So basically, all the shapes which you showed, all the shape of flowers and all the mathematical shapes which you use can be actually represented with any degree of accuracy using atomic functions. And this is it will be in my presentation, which will be next. So basically, there is a huge potential, because in your presentation you wanted to see new set of glasses. I'm showing you set of glasses. The atomic functions and your theory will be, maybe it will be very interesting research direction for future. Next one is the, regarding the Fourier series, So basically, you're trying to describe, you try to describe shapes, which is the, enclosed shapes, with the Fourier series. But Fourier series is it's a function which is defined everywhere. It's not a compact functions. So in Rvachev theory, there is a so-called generalized Taylor series, which is maybe more suitable. So it makes sense if it's a flower, for example, if it's a compact object, it's better to describe it as the compact objects rather than using Fourier series, which will, it's kind of looks for me a bit of unnatural. But anyway, presentation is exceptional, and there is a lot of potential, especially in the combination between your theory and what is Croatian school is doing in atomic functions. That's it.
And thank you for your comment, because this is really why I gave Ilse this talk, to see where there are convergences. So Johan Fougerolles and Vadim Shapiro pointed them out to me many years ago. Now, unfortunately, as I said, Johan, not fortunately for him, he followed his instinct and he started a restaurant. So it's good to connect with the originators of and people who know Professor Rvachev.
Yes.
Thanks.
Thank you, and I'm sorry. I suppose Professor Ricci was ready to make a comment.
Yes, please. But you have to unmute him, I think. Oleg, can you do that? Or?
Professor Ricci, kindly unmute yourself. Sorry. So sorry, could you unmute yourself once again? So sorry for confuse you.
Paolo, could you unmute, please? Paolo? We don't hear you.
Okay.
Yes,
I'm very happy to see John and Iliko, which are my best friends. I gave only the possibility, some small idea, and Johan developed them in very, very hard way. I'm very happy to see him. I'm not very able to speak like him, so I'm glad to hear his presentation. Thank you very much, Johan. No problem for me. Thank you.
Thank you. Also, Iliko is here. Ilya Tavkalidze from Tbilisi.
Iliko is also in. I saw him. Thanks a lot.
Yeah, I think Oleg also for the schedule. Yeah, I think we're running a bit over time. So
Yeah, sure.
so we still have this round table where we can discuss the ideas.
Okay, let's go on further. And the next presentation is the A-string functions in theoretical physics by Professor Eremenko. Professor Sergei, you're welcome.
Can you hear me?
Yes, you are audible.
Yes.
Can you see the presentation?
Yeah.
Yeah, all good. Thank you very much. So basically, I just want to just give you overview of the new scientific directions which I am working basically since last few years. Basically, the presentation called A-string functions in theoretical physics. First of all, some information about myself. I'm author of the 3 books, around 50 pages, papers and presentations. I'm pupil of the Rvachev, Vladimir Logvinovich. He was my teacher. So for years, I work in different areas in finite element methods for first part of my life, in natural vibrations of constructions, so this was I work for military industries, atomic power stations and so on. It was before I migrated to Australia. Currently, I'm living in Australia for 25 years. My recent book is a Soliton Nature. I also like nature a lot, and I do a lot of my book is dedicated to 200 in my book it's 200 photographs of waves and different wave patterns in nature. That's why I'm also a fan of exploring the nature and creating some theories for nature. I would like to, because this conference is dedicated to kind of memory of my teacher, and I would like to give you, few minutes, some basically some memories about my teacher. I met him first in 1984, and this is on the second photograph. He was about look like approximately like this one. It was probably a photograph from 1984. He was a lecturer in our university, in National Aerospace University, which is called now Kharkiv Aviation Institute. And I was visiting his lectures, but the story was he was doing lecture on the year 3 of applied mathematics, but I was actually in year 4. And in order to hear his lectures, I was skipping the lectures on economy and basically visiting his lectures, by skipping other subjects. And because of this one, I was in trouble, almost evicted from the university because I had a very bad marks in economics. But I was very fortunate to meet Vladimir Logvinovich, and basically on the lectures of him, which is unforgettable, I was asking lots of questions, and I bought his book. And then basically after lectures, he invited me to basically be his PhD student, and I kind of refused because my dissertation was almost ready. I defended my dissertation on the first year after university, And then I published my first book on the finite element methods. And then Vladimir Logvinovich invited me to be his doctorand, for the doctoral degree. And I went to, I defended my Doctor of Engineering degree in 1 year as well because of him, so and I had a very personal, close relationship with him. Recently, I published my memorabilia about Vladimir Logvinovich in a book, and he is kind of inspiration for my life. He was not only a remarkable scientist, but he was also very gentle and noble person to work with. And currently, this is the photograph on my room, with chessboard. Vladimir Logvinovich is always with me. I try to be even look like him on these pictures, basically. So it's I would describe him as one of the best person I ever seen in my life, probably the best person I've seen in my life. So I was very lucky to work with him. Anyway, let's go back to the presentation. I would like to tell you a bit more about the history of I-string functions, which is subject of my presentation. Basically, the theory of I-string functions started from this work, which was published in 2017. So basically, it's a new theory which I am working on, so basically, what is I-string function? I-string function, it's a kink-like function. Kink, this is on this picture we can see. This is the picture of kink. For example is a sigmoid. Sigmoid is a kink function. So what I did, I did computer experiment. Is it possible to find kink functions? What kind of kink functions? So if we add one function and another one, and if we add them together, so if, for example, we take one sigmoid and second sigmoid and add them together, is it possible to, so basically when we add in them, we usually have like a bump in the center, so that they're not perfectly fit to each other. And my question was, is it possible to find such a function that, so there won't be any bumps in between, so we can basically reproduce straight line by summation of the multiple functions. So summation of the same function, but it's shifted in a particular on the particular lattice. And this function was found, and this function looked like this one, which is called atomic string. I called it I-string, basically. And this function has a remarkable property. From these functions, from these kink functions, it is possible to compose straight line. But it's not only straight line. We can compose any by changing the parameters of this function. We can compose curves, a different curve, which is different curve functions and different shapes and so on. This is immediately basically. So basically, the idea is I-string function has been found in the computer experiment to compose a line and compose different curves. So this is basically in mathematical way, the problem of representing a line can be formulated as follows. So we need to find the function, which is called Metrian function. So we want to that exactly can reproduce straight line, which is x. So it's basically we want to find the function that we can use like from pieces we can compose a straight line. But what is important, the same Metrian function should be used for representing curved functions as well, not only for the straight line, but for any other curves, So the problem, if we differentiate these equations, the problem basically comes to if we found derivatives of this equation number one, we comes to the so-called partition of unity. So we need to find the function which performs partition of unity. And here, suddenly, after computer experiments, I found that, atomic functions, which is Rvachev taught me like 30 years ago, is a perfect candidate for from atomic functions. Atomic functions satisfy partition of unity. It means from atomic functions we can compose straight line, which is the constant. It means so for our function, metriant function, it's just the integral of atomic function. This is how atomic function was. This is how I-string function was discovered in 2017. So A-string function, next one I just want to show you is so basically, A-string function is basically integral of atomic function, which was discovered by Rvachev in 1970s. So basically, last year there was a 50 years of atomic functions, and as I mentioned, it satisfied partition of unity, which is important, and this is the most important results from the theory of atomic functions. So atomic functions, using atomic functions, it is possible exactly represent the polynomial of any order. So we can represent linear function, parabola, cubic parabola, and basically a polynomial of any order. And this is the very, very important property, very special property of atomic functions. This is why they are kind of brilliant and significantly different from polynomials and so on. So basically, and because atomic functions can exactly represent polynomials, it can also represent any analytic function. So analytic function is the function which is representable by the convergent Taylor series. For example, the sinus, exponents, all other functions, which is the well-known in geometry, including super formula of the, Johan, so it's so basically we can, so all these analytical functions can be represented by convergent series over the atomic functions, So this is the remarkable property from atomic functions, which is the, and these theorems was proven, by Rvachev and Vladimir Alexeyevich Rvachev for, probably 40 years ago. But what also I discovered that A-string function, which is the integral of atomic function, which I showed you before, it also, not only the integral, it is also composing the atomic function itself. So if you take, if you perform a computer experiment, for example, if you take one A-string function, and then we take another A-string function, and then we add them together, so we can exactly represent atomic function. So basically, basically there is this fundamental relationship between atomic function or Rvachev and A-string function, which was introduced in 2017, and this is the relationship. So this tells you that atomic function is a kind of composite object. It can be represented via the summation of the more simpler functions. It is also has the following application, that all the theorems and theories which is related to atomic functions, which has a 50 years of history, also applicable for A-strings. Whenever we got atomic functions, we can replace them with A-strings. And this is the very kind of generic idea. So basically, this is the, once I discovered, once I kind of come up with this one A-string functions, I start looking for different applications in different areas, which is I would like to show you in theoretical physics. First of all, what comes to my mind is it's called basically it's an idea of atomic solitons. Solitons, as we know, this is by the way, pictures from my book, which is recently published. So it's a solitons, as you know from it's like a theory of solitary formations. Here, for example, we can see the solitary wave in the ocean, which I pictured. This is another one. So it's a solitary theory of solitons is developing for 200 years, and all the solitons is described by nonlinear differential equations. Solitons are inherently nonlinear. So basically, what I discovered is that solitons is described by nonlinear differential equations. But if you take, for example, a string function, it is also described by nonlinear equation. This is equation nonlinear, but it's very special. So let's, for example, consider this formula. It's like a simple equation. Yeah. If for example, if this function is 0, we've got a constant. Solution is constant. If this function, for example, equal y, we've got a solution. It will be sine function. But if this function is sine from y, we are coming to this function arctangents of exponent, which is called Frankel-Kantorova soliton or sinus-Gordon soliton function. So we can see here, if you put nonlinear function, it is start describing solitons. But if we replace this nonlinear relationship with a more advanced relationship with shifted arguments, we are coming to a string function. So a string is also nonlinear function which satisfies nonlinear differential equation of special kind. And this is this idea basically prompt me to introduce the concept of atomic solitons. It was done in basically I published my paper in 2018, which is called atomic solitons. Atomic solitons is a new class of solitons. This paper is very popular on ResearchGate. There is multiple recommendations, and multiple readers. So this is the one of the extension of the theory of atomic functions of Rvachev to the new scientific domain of the theory of solitons. This paper describes very many different applications, which I don't want to go to this one, but let me continue with other type of physical problems. Another problem which is instantly come to my mind when I introduced a string function is the space-time physics and gravity and the basic curvature of space-time. The idea is obvious. If from a strings we can exactly reproduce straight line from the kind of solitary pieces, from the solitary kin functions, it invites idea of quantum. So basically if you consider this line as a space-time, space line, geodesics, this geodesics can be represented as a summation of the small pieces of the small ice strings. So this is instantly invites idea of quanta. So basically quanta of space. So basically we come here, in this theory we come to idea of the representing space-time from the A-string and atomic functions. So basically, if it's a uniform space-time, we can uniform space-time will be a combination of the similar A-strings, But if it's a curved space-time, so we need to change the coefficients, and we can reproduce. We can basically simulate curved space-time. Here we've got some examples. So it's for example, in this picture, curved space-time, represented via the atomic functions, which is introduced by Rvachev. So this is kind of theory is a combination of the general relativity of Albert Einstein and the theory of my teacher Rvachev. That's why I was so interested in this one, because it's a novel combination. No one has done it before, and currently I'm working in this area very intensively. I'm writing now a book, which is called Atomic Space-Time, and I'm putting together, mathematical theory, proper mathematical theory. And so this book, this theory includes 13 theorems, basically, which is based on the idea that using atomic functions, it is possible to reproduce any analytical manifolds, any analytical functions, and the same idea is used here. So basically, I proven few theorems, which just tells that, for example, Ricci tensor and Christoffel operators in Einstein equations, they preserve analyticity, and basically they are representable via the convergent series of the atomic and string functions. So basically, the final idea is the theories of Einstein and Rvachev and atomic functions, I-string functions, can be combined, and I-string function and atomic function can describe a so-called quantum of space-time, because they are naturally, atomic function, for example, it is naturally localized. It means it's a local, it's a quantum, it's a function which is defined in a local area. And from the translations of these functions with different parameters, we can reproduce gravity and reproduce equations. Here we've got some examples, for the representation of the some known solutions of general relativity. For example, Einstein-Minkowski spacetime, which is flat spacetime, can be presented via the A-strings, which is very obvious way. It's a sum of the same functions. In Friedman's solution of the expanding universe, we've got analytical functions, which is called R sine screwed. This function, it's a 10.37. So it's this function we can see is also analytic function represented by convergent Taylor series. It means it is definitely reproducible by the, it basically can be presented as a summation of the atomic and string functions. Another solution is a Schwarzschild solution for the black holes. It also includes two analytical functions, first and second one, apart from the point of zero. And it means it is by the theorems which is proven, it can be also represented via the atomic and string functions. And here is example, for example, here we are representing Schwarzschild metric functions with the 8 A strings, so it's basically, I've done computer experiments and programs which is can be, I can represent, different shapes, with the A-string or atomic functions. Here, an example of the cubic parabola. Cubic parabola, in some areas can be also represented via the A-string and atomic functions. So basically, what it leads, because space-time, since Einstein, gravity, it's a curvature of space-time. If we can describe the curvature of space-time with atomic and string functions, it means we can formulate new theory of, atomic gravity or string gravity, where a string and atomic functions represent the, fundamental building block, elementary quantum of the space-time. So the theory is basically is uniting idea of multiple scientists. Of course, it's Einstein. Now the theory is unites, Einstein theory with the theory of my teacher Rvachev. I also had a huge influence by Stephen Hawking. All this with his idea of space-time distortions. because atomic functions and string functions are so it's elementary space-time distortion. That's why for me it was very important. Also, I'll show you later, how we can represent Higgs fields and so on. And also I would like to, one of my pantheon of the, heroes, it's Albert Weinik, it's a Belarusian scientist who introduced the concept of metrions, metrions at the quantum of space-time, and Vladimir Logvinovich, and myself, we discussed Weinik series, for some, a few decades back, so it's so basically this is the important theory on I'm working on, and I'm writing now a book, and hopefully, it will be fruitful, Next one is the fields quantization. So it's not related to the space-time, but to the fields. In current physics, the main theory of current physics is the quantum field theory. In quantum field theory, any field, any particle, is actually a field. And this is very good for the theory of atomic functions. So representing of the particles as a fields gives idea of the application of atomic functions. Basically, this is an example, for example, Higgs boson. This is the example of the Higgs boson, how it's represented, in modern quantum field theories. It represented as like a solitary spike. And what I suggest is to use atomic functions to describe the elementary space-time distortion, elementary block of the Higgs field. So it's because the beauty of the atomic functions that if you've got Higgs field, which is smooth field, can be represented via the smooth functions. It means smooth analytical functions. It means it can be represented via the atomic functions. It means atomic function can describe elementary particle of the Higgs field and all other fields. This is a very powerful idea. So atomic functions became not only a mathematical object, abstract mathematical object. It became a quantum of the particular fields. Basically, what I'm trying to come up with the idea, exploring the idea that if multiple fields, for example, space-time fields, Higgs fields, zero-point fields, electromagnetic field, can be described by the same method via the atomic and string functions, it means there is a very powerful idea of unification of fields. So maybe all the fields which we are, all the fields we are experiencing, is basically has a common, common building block, common mathematical building block, and so it means atomic functions and string functions can actually represent fundamental universal mathematical block from which everything is made of. In Rvachev, he called atomic functions, basically as a mathematical atoms. And what I'm suggesting, idea that these mathematical atoms can describe any field. It means so we can potentially consider atomic and string function as a mathematical building block from which everything is made of. So this is the kind of theory which is I'm trying to to develop these days, and it is still work in progress, still many many stumbling blocks. Especially I've got kind of kind of big problem with the, publishing these theories, because I'm not actually a physicist, and I'm trying to describe, physical concepts like Higgs fields and so on, and basically, but I'm actually mostly kind of applied mathematician, and for me to publish, papers on physics, it's also quite problematic, but I'm basically working on this one. Next, I would like to show you some information about my book. So it's in 2021, I published a book which is called Soliton Nature. I also like, nature a lot, and, I'm basically observing nature for many, many years. And I would like to, basically gives you, so in this book, I used 200 images, which is I photographed, images of waves, different kind of waves in nature, and I try to publish very easy to read popularization book, which is called Soliton Nature. And I would like to, show you, for example, this book is available on Amazon, in any country in the world. It has a absolutely magnificent, beautiful pictures of waves, different kind of waves and fields. It also describes the theory of atomic functions, but, so part of my passion is also observing nature and creating like a different theories of nature. This is the idea. I would like to offer my book to every participant of this conference. If you can give me your postal address, I'll post to you, magnificent, beautiful book. And I hope it will be interesting reading. The book has, exceptional photos, which I photographed for many, many years in different countries, and so on. So that's it for my presentation. For brief overview, please contact me. In presentation there's my details, my ResearchGate products, and so on. And thank you very much for your attention.
Thank you, Professor. Any questions, or maybe some comments or remarks, or a little discussion? Professor Gielis?
Yeah, just thanks for your excellent presentation. Yeah, I would just like to comment. I think there are very interesting ideas. I hope we can communicate on this. But it will be interesting to see all physicists are looking at discrete stuff, and I'm looking at continuous, let's say, representation of nature. So it's going to be an interesting discussion. That being said, continuous and discrete are just two sides of a coin, in my opinion. So
yeah, I would like to show you something. I also published, on YouTube, I published a video channel. I just want to show you, if you go to YouTube, and can you see my screen?
yes.
So if in YouTube, if you type Soliton Nature, Soliton Nature, we've got, I published magnificent videos about the, different kind of grid waves, which as I photographed, so it's absolutely, beautiful natural phenomena, which is I, photographed for many years. So it's next one. So I've got multiple videos of here, different kind of waves, yeah, and just a second. Yeah. So this is the different type of waves on the beaches, which as I photographed myself, so for a long time. Another, Johan, you like, I know you like to understand how nature works. I published recently interesting video on the shapes of the some mountain ranges, so it's a,
Yes, I already explored your video channel and your mountain ranges.
yeah.
So
Yeah. So basically, this is the idea that the mountain ranges has a shape of waves. So it's a very interesting, kind of observations of nature, and mathematical theories.
Thank you. Thank you. Let us go on further because we are in time. And the next presentation is the rational approximation of the atomic functions by Budunova Kristina. And she noticed that her internet connection is not stable. So it might be some issues. So let's see. Anyway, Kristina, are you with us? Are you ready? Okay, I suppose she disconnected for some reason. Okay, let me call her. Just a second.
Hello.
Hello, Kristina. You are audible.
I have very bad internet connection.
Yeah, that's a pity.
Hello, dear participants of conference. I am Kristina Budunova, a junior researcher of Kotel'nikov Institute of Radio Engineering and Electronics. I am assistant of Professor Viktor Filipovich Kravchenko.
Kristina, I'm sorry, your presentation is not visible. Professor Sergei, let me ask you to close your demonstration for a while. Professor Sergei?
Can I begin?
Thank you. Yeah, Kristina, go ahead.
My research is mainly related with Kravchenko-Kotel'nikov theorem and its practical applications. The Kravchenko-Kotel'nikov theorem is a generalization of the famous Whittaker-Kotel'nikov-Shannon theorem on signal recovery. The basis functions of Kravchenko-Kotel'nikov series are shifted spectra Fa of t of atomic function HA of x. Due to faster attenuation of functions Fa of t, truncation error of Kravchenko-Kotel'nikov series is much lower than truncation error of Kotel'nikov series. The formula for the upper bound of the error shown on this slide was obtained in 2018 year. The natural application of Kravchenko-Kotel'nikov theorem is signal filtering. Some properties of HA of x function allow us to consider it as a magnitude response of an ideal low-pass filter with faster attenuated impulse response. Indeed, HA of x is compactly supported function. Then A is greater than 2, HA of x is equal to constant in the central region of its support. In addition, HA of x is infinitely differentiable function. Hence, its spectrum has fast attenuation. Thus, was standard the problem of filters with magnitude response on function HA of x design. The first was solved the most simple problem of filters with finite impulse response design. The problems of construction analog and digital IIR filters were much more complex. The solution of these problems requires the presence of the method of atomic function space approximation with rational fractions. Such method was proposed in 2020 year. It is based on the formula which follows from the Cauchy integral formula and holds for any entire function. As the entire functions, we use the partial Fourier sums of phi f of omega function, which is the square of normalized HA of omega function. To obtain a rational fraction from the formula, we can replace integral with Riemann sums. Consider as an integration control an ellipse with center at the origin that passes through points plus minus 1 and plus minus JB of complex plane, where B is parameter. For the chosen integration grid, the rational fraction HBM would be a real fraction with numerator and denominator containing equally even powers of omega. The uniform error depends on integration contour, that is from the parameter B, and the number m of partial sums, phi am of omega terms. Let's concern the finite set of numbers m. The method of real fractional approximation search was proposed in 2020 year. For every fixed term, we can search the solution of problem with gradient descent method, and then we can apply brute force search over numbers m. However, such method does not necessarily provide the non-negative rational solution. Moreover, we search the solution or the semi-axis b greater than 0, and hence the solution may not exist. Here are presented some obtained last year advantage for the method. The method for the search of non-negative fraction approximation was proposed and theoretical background. 3 theorems was proved. The first 2 theorems are about the bound or the finite interval where we must search the solution. We need an approximation with fairly small error. Setting some error epsilon 1, we can define the interval out of which the error epsilon is greater than epsilon 1. Since we have now a closed finite interval where the error is continuous, then the solution exists. The third theorem is about the reduction of continuous problem to a discrete one. If we set any value epsilon 0, we can select grid on the interval B0, B1, such that the solution of discrete problem differs from the solution of continuous problem no more than 1/10 of epsilon 0. As the value of epsilon 0, we can set the value of the error obtained with gradient descent method. Now we have the finite set of points where we perform the solution search. Checking for every point the non-negativity condition, we can find the best non-negative solution if it exists for a given m. On base of non-negative rational fractional approximation, we can construct an analog filter with magnitude response on atomic function h of x. That filter can be applied, for example, in digital to analog conversion for recovering the signal from its samples. There are the impulse responses of atomic and classical Butterworth filters of 30 order. The results of signal reconstruction by its first 25 significant samples using atomic and Butterworth filters are shown here. And it is a result of reconstruction from the set with first 10 samples discarded. It can be seen that atomic filter turns out to be insensitive to samples discarding. A significant error was obtained when applying classical Butterworth filter, which magnitude response approximates a rectangular pulse. We also note that the method allows to obtain the filters with magnitude response on base of an arbitrary non-negative compactly supported functions with fastly attenuated Fourier transforms. Here are shown the B-spline B2 and relevant filter magnitude response. On base of described analog filters were obtained digital filters with infinite impulse response. The digitization of analog characteristics was performed with impulse invariance and bilinear transform methods. The obtained and numerical experimental results of digital signal recovery are shown here. We can see the same error for classical IIRR filters and same insensitivity for atomic ones. Here are some references on atomic filters and on Kravchenko-Kotel'nikov theorem. Thanks for your attention.
Thank you, Kristina, for short communication. I suppose we are in time still. So, any questions?
Yes, please.
Yeah, welcome.
Hello, everybody. I'm Viktor Makarichev. I was PhD student of Vladimir Alexeyevich Rvachev. And I have a question to Kristina. Tell me, please, did you or maybe one of your colleagues study approximation properties of spaces of the function h, which is considered in your presentation? Maybe you try to prove some theorems about best approximation of some classes, for example, Sobolev classes.
No, we don't try to perform it.
Okay, thank you.
Thank you. Any more questions? Yes, welcome. Vasily would like to ask. Welcome.
Thank you. Hi, everybody. I would ask about maybe you trying to make digital realization of your analog filter based on atomic function. Yes or
yes,
no?
Yes. I would like to show a poster about it.
Thank you. Thank you.
Yes. There are digital IIRR filters, filters with infinite impulse response on analog filters. Do you see?
Thank you, Christine. Thank you.
This is magnitude responses of these filters. It is obtained with bilinear transform and impulse invariance methods. And there is a result of numerical experiment with digital signal recovery. These are results for classical Butterworth IIR filter, and it can be seen that there is great error, and this is a result obtained for atomic filters, and it is insensitive to samples discarding.
Thank you. Any more questions? I suppose everything is fine for everybody. So thank you, Kristina, once again, and thank you for your presentation. Right now, we completed the first part of our seminar. So we have some, let's say, extended break till for about 45 minutes, roughly speaking, till 1:30 in European time zone. So let's see in 45 minutes, okay? See you in 45 minutes.